In this video, we'll revisit Noether's theorem to find out what happens when time is a continuous symmetry of the system. We'll discover a conserved quantity that we call the Hamiltonian. If time is a symmetry of our system, that means that the Lagrangian is the same now as it is delta t from now. Instead of reparametrizing the coordinates like we did for spatial symmetries, we'll look at the total derivative of the Lagrangian with respect to time to see if we can derive a first integral from there. The total derivative of the Lagrangian with respect to time is given by the sum on I equals 1 to d, where d is the dimensionality of the system, of dl by dqi times dqi by dt, plus dl by dqi dot times dqi dot by dt, which is dqi double dot, plus the partial derivative of the Lagrangian with respect to time. This last term is 0 because we know that the Lagrangian doesn't change with time. We'll use the Euler-Lagrange equations to simplify this term. dl by dqi is equal to d by dt of dl by dqi dot. But based on our definition of generalized momentum, dl by dqi dot, we can identify dl by dqi with the rate of change of the generalized momentum, which is pi dot. Then the derivative of the Lagrangian with respect to time equals the sum on I equals 1 to d of pi dot times qi dot plus pi times qi double dot. And we'll use our favorite trick from this unit, which is undoing the chain rule, to rewrite this as d by dt of p dot q dot. So the combination of terms p dot q dot minus the Lagrangian doesn't change with time throughout the dynamics. That means it's a constant of the motion. This constant of motion is quite famous and gets its own name. This is the Hamiltonian, the sum on I of pi qi dot minus the Lagrangian. If the Lagrangian does not depend on time, then the Hamiltonian is a conserved quantity of the system. So what is the Hamiltonian? If the Lagrangian doesn't depend on time, then the Hamiltonian is just the total energy of the system. To show this, let's look at the transformation between Cartesian coordinates, r of q, and generalized coordinates, q as a function of r. In Cartesian coordinates, the kinetic energy is 1/2 m times r dot squared. Let's look at r dot in terms of the q's. Ri dot is equal to the sum on j of dri by dqj times dqj by dt, which is just qj dot. Then r dot squared is equal to the sum on j of dr by dqj times qj dot dotted into the sum on k of dr by dqk times qk dot. To make this easier to write, I'm going to call this term a sub j and this term b sub k. Then my kinetic energy in terms of my new coordinates is 1/2 m times the sum on j and k of aj dot bk times qj dot times qk dot. Our goal is to write down the Hamiltonian in terms of these new coordinates. First, we need to write down the generalized momentum I in terms of these new coordinates. And that is given by the derivative of the Lagrangian with respect to qi dot. And since we know that potential energies can't depend on qi dot, this is equal to the derivative of the kinetic energy with respect to qi dot. And this is equal to m times the sum on k of ai dotted into bk times qk dot. Then the sum on j of pj times qj dot is equal to the sum on j of m times the sum on k of aj dot bk times qk dot times qj dot. And you'll notice that this is just twice the kinetic energy. Then our Hamiltonian is given by the sum on I of pi times qi dot minus the Lagrangian. This first term is twice the kinetic energy, and the Lagrangian is the kinetic energy minus the potential energy. So when the Lagrangian doesn't depend on time, the Hamiltonian is the kinetic energy plus the potential energy, which is just the total energy of the system. Let's compare and contrast Lagrange's method and Hamilton's method. The Lagrangian is a functional of generalized coordinates q, q dot, and time, and is equal to the kinetic energy minus the potential energy in those coordinates. The Hamiltonian is a functional that depends on the generalized coordinates q and the generalized momenta p, where the generalized momenta are given by dl by dqi dot. The generalized coordinates we use to describe the Lagrangian define a configuration space. Every point in that space defines the state of a system, which are the positions of particles and their velocities at any snapshot in time. The combination q dot is called a state space. Lagrange's equations give a path called an orbit through state space. Lagrange's equations are second-order differential equations for the coordinate q. Hamilton's method is a little bit different. Our functional depends on both position and momentum, and this combination of position and momentum defines what we call a phase space. Hamilton's equations give trajectories of these particles in phase space, and they simultaneously evolve both the positions and the momenta of the particles. Thanks for watching, and I'll see you next time.